membrane in a couple of confined spaces here, the individual molecules, if you could number them from 1 to 12, one might be on this side, then it'd be over here, then it'd be over here, then it'd be, back and forth, back and forth. The individual particles would be constantly changing place, and yet the process of diffusion would be moving in a definite direction. Well, what definite direction is that? From high to low concentration. And so if you got them all on one side, so there's a high concentration, there's a lot of them over here, a few of them over there, diffusion will scatter. Now, bring them back together to where they're far more scattered out. How long would I have to shake the box until all 12 of the particles were back over on the right side and stayed there? Now notice, million years, billion years, gazillion years, infinity, it doesn't make any difference. The process doesn't move in that direction. They might momentarily, all 12 of them wind up here, but by the time you said, oh, they'd already be scattered out again. And so this process of diffusion goes from where there are things packed together to where there are things scattered out, from high concentration to low concentration. It tends to scatter things out. And so it's a one-way process with time. Well, now you can throw in a little bit more predictability. It also depends on how big the particles are. In fact, this is a crude way of estimating molecular weight of particles, is just to see how fast they diffuse. The bigger the particle, the slower it diffuses, and the molecular weight is basically, the square root of the molecular weight is proportional to the diffusion speed. And so you can actually calculate roughly how big a particle is from how fast it diffuses. And it goes to a definite end point. And so here we're talking about individual molecules moving chaotically, and yet you've got a high degree of predictability and order in a sense right now. It goes in one direction from high to low. It goes at a rate that depends on the size of the particles and the temperature. And it goes to a definite endpoint. That is, it goes to equal scatter. You can say, as I'm shaking them back and forth, diffusion has ended. On average, there's 6 on each side. 8, 4, 7, and 5, 5 and 7, but on average 6 on the side. So diffusion has ended, but random molecular motion continues. Well, even that, God is able to capitalize on that chaos. And that's fairly phenomenal. A lot of phenomena on living things depend on diffusion. And you might think, well, it's almost contradictory. Living things are characterized, by a high degree of order. Things go on in a definite direction at a definite rate to a definite endpoint. And yet, diffusion is based on molecules just blindly, flailing around, not planning to go anywhere. And yet, that very simple process right there is what's required to get oxygen from the lungs into the blood. And so, as you breathe in, the air that you breathe in is about 21% oxygen. The blood that's coming back to the lungs, the oxygen that was carried by the blood has been used up by cells for metabolism, burned for energy, and things like that. And so the blood that's coming back into the lungs has less oxygen in it than it did before. And so as a result, oxygen molecules have no clue. When you breathe in oxygen molecules, they have no built-in desire to find a blood vessel and jump in, grab hold of the hemoglobin molecule. They're not looking to go anywhere in particular. They're just scattering out blindly. But as a result of that blind scattering out process, they're going to move from where there's a lot of them inside the air sac and the lung to where there's far less of them in the blood. And so they'll automatically diffuse in the designed direction. Well, now, as you might imagine, diffusion is not a particularly rapid process. And so if if I want to go from here to the piano, I can walk in a straight line. And so you can kind of figure out how long it would take me to get there. But supposing instead, you blindfolded me, spun me around, and I just had to wander about at random until I got to the piano, I'd eventually get there, but it'd take a lot longer. And so diffusion takes a long time. Well, the blood is only in the lung for a fraction of a second. And so if you're going to load up the blood with oxygen, the distance between the air sac and the lung is crucial. It's got to be at the right distance for diffusion to be able to fill up or saturate the blood with oxygen. Guess what? The distance is ideal. And so you have the real thin walls of the air sac right next to the real thin walls of the capillary with just a little bit of space in between them in the normal situation. What happens if that distance between the air sac and the lung increases? Death can result. Illness can result for sure. What can make that happen? Well, a variety of things, and of course some kind of lung infection, some kind of pneumonia. If you get a bacterial infection in the lung, then of course white blood cells come in, it tends to swell up and so on, fill with fluid. And so the distance between the lung and the blood is too great for the oxygen to get across. So you can suffocate, from pneumonia. You actually die of suffocation in a way. Well, what can you do about it? Well, of course, you try to use antibiotics to get rid of the bacteria, to reduce the inflammation so that the membranes come closer together, and you use oxygen. In the old days, they used oxygen tents. Now they have other ways to increase the oxygen concentration. Then the more molecules trying to get across, even if the distance is too great normally, they'll still get across to keep you alive long enough for the antibiotic to work. And so it's very crucial, to have those distances exactly right. And that sets, you may wonder, why are cells a certain size? And so there are maxima on how big a cell can be based on can materials that need to get from the outside to the inside of the cell, can they get there by diffusion fast enough? Plants have a way to compensate for that. They're bigger, than the average animal cell, but they have a stirring rod, so you can put a lump of sugar in a cup of coffee, and you wait for it to, if you just take a sip, it's bitter from the top, the sugar's still down the bottom. If you wait long enough, the water molecules will pound the sugar cube to pieces and eventually spread it throughout the cup. But if you don't want to wait that long, what do? Take a spoon, stir it up, and instantly it's like that. Well, plant cells have cytoplasmic streaming. Their insides actually continually circulating, and so they can maintain a larger cell size than animal cells can that don't have that internal stirring rod. And so there's all kinds